Here are solutions to homework set number 12 for 463-1663 Modern Control. This homework set looks at designing feedback controllers using linear quadratic Gaussian loop transfer recovery, or LQG-LTR. So here's the idea. Given a plant, in this case I've got a cart and pendulum system, I've got the dynamics, we covered that earlier, like in homework set number 4. Make this plant behave like a reference model. So here's the model, that's how I want it to behave. With LQG-LTR, what you do is you define the reference model, that's how it should behave. Here's the plant. Come up with your feedback gains, Kx for the plant, Kx for the model, and I'm going to use LQG-LQR techniques to find the feedback gains where the weighting is the error between the two. As the weighting on the error goes to infinity, the two should track. So to do that, I first set up the state space model. Here's the augmented system, plant, reference model. It's A matrix, B matrix with respect to U, B matrix with respect to R, and the output, E, is just Y minus Ym, Cx minus Cmxm. As I crank up the gain on Q from going to infinity, I get better and better tracking. And to show that, that's probably easier to see in MATLAB. So here is my M file. I'll define the plant dynamics, the reference model, that's what I want, pull out the ABC matrix, form the augmented system. My output is just Y minus Y model. Q is just C transpose C, and the weighting on Q dictates how well it tracks. As the weighting, this number right here, goes to infinity, the tracking gets better and better. So start with a gain of 100. At 100, the output is the red, the pink is the reference model. Weighting of 100 doesn't track real well. Crank up the gain, make this 10 to the 4th, which would be 100 e squared, 100e parentheses squared. So there's your 100 squared, 10 to the 4th. Tracking is better. Make the weighting 10 to the 6. And what you should see is the gain gets higher and higher, tracking gets better and better. That's the LQG-LTR. The loop transfer recovery is as I let the gain go to infinity, I get better and better tracking. Now in the homework you just had to stop at 10 to the 6. If you kept on going, let's make that 10 to the 10th. Actually may have gone unstable. I'm getting numerical problems if the gate gets too large. Let's try 8th. There we go. So that's the LQG-LTR just with a plant. Now one problem is you notice the DC gain isn't 1. I can adjust for that by throwing in a prescaler, but if the plant dynamics are slightly wrong, that constant will be a little bit wrong as well. A second form is to add in a servo compensator. So with the servo compensator, what I do is I integrate the difference between the two. What that does is that forces the DC gain of the plant to match the DC gain of the reference model. So if I give it a step input, it will track at DC. Now same approach. I find the feedback gains, Kx for the model, Kx for the plant, Kz for the servo. Find all those feedback gains to minimize, in this case, Z squared, this servo compensator's output. So to do that, I form the augmented system. Here's the plant, servo compensator, reference model. It's A matrix, B matrix with respect to U, B matrix with respect to R. The feedback gains that I try to find using LQR techniques are found again using LQR as the weighting goes to infinity. So again, kind of similar. Here's your ABC for the plant, the reference model, the augmented system. The thing I'm weighting is actually just the servo state, just z. As that weighting goes to infinity, I get better and better tracking. So if I start with a gain of 100, or 10 times z squared, here's the tracking, and note that the DC gain is now 1. That's the property of the servo compensator. The tracking isn't great. And the blue line is the actual output. The green line is what it should be. Crank up the gain. It's now tracking better. And higher gain should track even better. So that's LQG LTR. As the gain goes to infinity, I can force the plant to behave the way I want. There is a caveat. I am getting fairly high gains, and it's just not tracking all that well. Part of the problem is the plant is non-minimum phase. To go left, I first have to go right, get the pendulum to start leaning, and then come over. So the reference model isn't really the best. It's also a fourth order plant, well, fifth order with a servo compensator, trying to make it behave like a second order reference model. So if I did minus 0.5 plus minus j1.3, I could actually do a little bit better. This isn't part of the homework, but in practice what I would do there's my desired response. Those two poles, it's really a fifth order system though. It's a whole lot easier making a fifth order system behave like a fifth order system. So let's maybe have a couple more poles, minus 2, minus 3, minus 4. So now we have fifth order reference model. Make the DC gain 1. I now have a fifth order plant behaving like a fifth order reference model. So once I get the code debugged, that's how it works. And the red is the plant, pink is the reference model. The plant actually has undershoot. Can't really avoid that. The reference model doesn't do that. If I were to add a 0, non-minimum phase 0, and get that just right, then the plant and the reference model both experience that non-minimum phase characteristic. Seems like a better response. And it seems much happier with that reference model. What that also does is that it gives me smaller feedback gains, better tracking. Again, not part of the homework, but if you play around with the reference model, take into account how the plant really wants to behave, I can get that response using less effort. But the idea behind LQG LTR is I can specify the reference model, and that'll tell me how the plant will behave, which is kind of neat because, again, what we've been doing before, I could use guessing, try to play different feedback gains, try Q&R to get the desired response. Here I can do that in one shot, just specify the reference model, and voila, there's your response. That's LQG LTR. And homework set number 12 for modern control.